Hello, welcome to Beginning Engineers. Today I'm going to be talking about economies of scale. More for less. What are economies of scale? Doing things more efficiently as output increases, leading to less cost per unit. In microeconomics, economies of scale are the cost advantages that enterprises obtain due to their scale of operation, typically measured by the amount of output produced, with cost per unit of output decreasing with increasing scale. At the basis of economies of scale, there may be technical, statistical, organizational, or related factors to the degree of market control. And that definition was pretty similar to doing things more efficiently as output increases, leading to less cost per unit. Here's another definition. Economies of scale are cost advantages reaped by companies when production becomes efficient. Companies can achieve economies of scale by increasing production and lowering costs. This happens because costs are spread out over a larger number of goods. Costs can be both fixed and variable, and you can see in the image on this slide, that line is the long run average cost, and see how it goes down from left to right as the x-axis, the number of units produced, increases, the y-axis value, the cost, decreases. That is economies of scale represented graphically. These economies of scale can be reaped for quite a while, but there are scenarios where you are producing too much and the costs actually increase per unit at exorbitant amounts. That is why the graph goes back up. Let's go over a basic example of economies of scale, and this is probably similar to something you did while in school. Let's say we have a company that manufactures a variety of custom silverware for large restaurant chains, using a combination of stamping, finishing, and plating activities. Currently, the company is under contract with one restaurant chain to manufacture 100,000 pieces of silverware for them. Let's say the restaurant is replacing the silverware in their older locations. This contract requires the manufacturing company to buy custom stamping molds and a few new pieces of finishing equipment to handle making these pieces. These are fixed costs. Fixed costs, also known as indirect costs or overhead, are expenses that are not dependent on the volume of a good produced or service provided. If you buy a new stamping mold or a new press, it doesn't matter how many parts you make on it. The price of that mold and the price of that press are static. They're constant. They are fixed. But the cost for the steel coil, employee labor, electric use per machine uptime, packaging, these are all examples of variable costs that are dependent upon how many pieces of silverware are made. A variable cost is a corporate expense that changes in proportion to production output. Production goes up, variable costs go up. Production goes down, variable costs go down. I made a table and graph based on different sized contracts, so you can see 10,000, 20,000, 30,000 contracts, on and on and on, up to 100,000 unit contracts. You can see in the fixed cost column, that value, $100,000, stays the same no matter how many units you are producing, because you still have to buy the equipment to make those units. The variable cost per unit is always 15 cents per unit. This covers things like the cost of the steel coil per unit, the labor per unit, the plating chemicals per unit. This is always the same per unit because the more units you make, the more plating chemicals, the more steel coil, and the more labor is needed. Adding together our fixed cost plus our total variable cost, and then dividing by the number of units, we get a cost per unit. And you can see it decreases as you produce more units. This is because the total fixed cost is getting divided out between more units, so the cost per unit is less. And you can see in that final column, I said the percentage of the cost per unit that is from fixed costs, and see how it goes down as well. If the restaurant customer saw that the silverware manufacturer offered a cheaper price per unit for 250,000 units, Then they may decide to go ahead and replace the silverware for all their locations. In that scenario, the silverware manufacturer can sell 250,000 units for a cheaper price and still have the same margin, or perhaps even a higher one, because their cost per unit falls from what it is when producing 100,000 units. So you can see on my table at the bottom, the cost per unit will drop from $1.15 at 100,000 units to just 55 cents at 250,000 units. So if at 100,000 units, the manufacturer sells them for $1.50 each, that's a 35-cent margin. At 250,000 units, they can sell them for $1 each, and that's a margin of 45 cents. That's an even better margin for them, but a cheaper price for the customer. This is one of the reasons you'll see a bulk discount, where in purchasing more, you pay less per unit. Economies of scale are not returns to scale, and there is a small distinction here. Economies of scale refer to unit cost and how this changes based on scaling efficiencies, whereas returns to scale is the relationship between the inputs and outputs over time in production. If inputs are doubled and output is doubled, returns to scale is the same, even if the cost goes down and there are economies of scale. If inputs are doubled and outputs triple, returns to scales are increasing, even if the cost per unit stays the same. So you can see how these two concepts are similar and that they both talk about scaling, but they are talking about different things. Let's talk about the determinants for economies of scale. We know that economies of scale exist, but what actually is it that makes the cost per unit fall as production volume increases? I think the first one we are going to talk about is the most engineering heavy, so it's very appropriate for this channel. Physical and engineering basis, economies of increased dimension that lower capital and operating costs. Some of the economies of scale recognized in engineering have a physical basis, such as the square-cube law, by which the surface of a vessel increases by the square of the dimension, while the volume increases by the cube. This law has a direct effect on the capital cost of such things as buildings, factories, pipelines, ships, and airplanes. What is the square-cube law? It is a mathematical principle first described by Galileo, which describes the relationship between a shape's volume and surface area as a shape's size increases or decreases. The ratio between the two volumes, the larger object and the smaller object, is greater than the ratio of the surfaces between the larger and the smaller object. So basically, as a 3D object grows, its volume grows by more than its surface area. So if you have a square with a length of 2 feet, that square has an area of 4 square feet. If we increase that length to 3 feet, the square now has an area of 9 square feet. But think about a cube. If a cube has a length of 2 feet, the volume of that cube is 8 cubic feet. If we increase that 2 feet to 3 feet, the volume of that cube is now 27 cubic feet. This cube-square law matters for economies of scale because in many situations, the cost of producing at capacity is proportional to surface area, whereas the output is related to the volume. A great example of this is pipes. The cost of pumping material through a pipeline is proportional to the circumference of the pipe and distance traveled, but the amount of the liquid that can be pumped is based on the pipe's volume. Because the volume of the pipe increases faster than its diameter, the cost per gallon pumped decreases as the pipe's circumference increases. This is because, like I touched on in my pipes video, you typically purchase pipe based on circumference and thickness of the wall of the pipe. You don't buy pipes based on the volume they can pump. That might matter on your specification side, but that's not how you are purchasing it. You are purchasing it on circumference and wall thickness, which is called schedule. So because of that, your cost does not increase as fast as your gallons pumped increase, which means you can pump more for less. Other real-life examples of the cube-square law include the strength of support beams increases with the cube of their thickness, Drag loss on ships and planes increases less than proportional with their volume, which means less fuel per volume of cargo. Also, heat loss follows a similar relationship, so in situations where retaining heat saves energy costs, there is a benefit in per unit cost and scaling machine or plant size. An important note here, don't mix up utilization with economies of scale. Upgrading your pipe size won't lead to any lower cost per unit if you weren't fully utilizing the smaller pipe anyway. Another determinant for economies of scale is economies in holding stocks and reserves. As quantities scale, the reserve stock needed for emergency situations becomes smaller in proportion to the units produced. Think about if you run a small machine shop that has 6 presses. You may have 2 of the critical pieces for those presses on hand to be ready in case some of the presses break. But now, if you scale up your shop to 15 presses, maybe you still only need 2 emergency pieces, or maybe you upgrade to 3 or 4, which is still smaller in proportion to your total number of presses. If you have more presses because you're producing more now, that means your emergency stock costs are smaller in relation to your quantity produced than they were previously. The next determinant is transaction economies. As production scale increases, the producer will have better bargaining power with their suppliers when purchasing raw materials. The suppliers themselves benefit from economies of scale and can sell more goods for less. Also, if you're ordering more raw materials, you can better establish supply contracts, which reduce any miscellaneous fixed costs in the PO and billing process. There are also managerial economies. Most functions performed by managers are cognitive and do not require resources, meaning as the scale of production increases, the need for more managers does not scale proportionally. But as you do take on more managers, if a certain manager is more successful, you can copy what they are doing and train your other managers, further increasing your managerial economies. Think about if you have a manufacturing plant that runs 3 shifts a day, and only the first shift produces a large volume and is fully staffed. If your facility takes on more work on the second and third shifts, you likely just need more material and machine operators. You don't need to hire more managers. The managers can handle more employees on shifts 2 and 3 because your managers on the first shift are doing it. You can also gain economies from the balancing of production capacity, line balancing. So it is possible that with a larger scale of production capacities can be used more efficiently, although much of it depends on how divisible or scalable the input materials and labor hours are. High production can allow for less changeover activities and machine idle time if done properly. In addition, any line balancing efficiency a process engineer puts into place is multiplied by each part produced, so higher production equals greater savings from efficiency. That time saved on a few parts adds up when those become thousands or millions of parts. I have an overly simplified example on the bottom of this slide. Let's say a small CNC shop is comparing the labor and efficiencies involved with producing 9,000 or 18,000 parts. There are 3 unique CNC machines needed to produce the part, and each machine has its own rate of production. The facility only has a single shift, so each machine keeps its tools and settings set up until the job is changed. Job changes can be up to an hour for each CNC machine, and often multiple CNC machines are needed to completely finish a product. You can see that if CNC 1 produces 300 units an hour, CNC 2 produces 150 units an hour, and CNC 3 produces 200 units an hour, that for the 9,000 part contract, it takes approximately 75 hours in the shop to produce all the parts. Of course, there's more labor hours because you have an operator on each machine. I marked when each changeover occurs for each CNC machine, so you can see that CNC 1 performs the changeover much earlier than CNC 2, which in turn is earlier than CNC 3. So, for those 75 hours, CNC 3 is running the entire time, but your first operator and then your second operator become available sooner. But if CNC 3 is needed for a different part, it won't be available until after the 75 hours. At 18,000 parts, it's still a similar story, but now we need 120 hours to produce the parts. But you'll notice with this contract that CNC 2 and 3 both change over at the same time, which means both those operators are working in tandem for the entire process. This could lead to more efficiency in the shop. Also, keep in mind that the changeover takes time, so you have to pay those employees for that labor. You're going to do the same amount of changeover, whether it's 9,000 parts or 18,000 parts. So the changeover costs are a smaller portion of the bigger contract, another efficiency to bigger production schedules. Another determinant for economies of scale are economies resulting from the division of labor and the use of superior techniques. A great example for this would be the Ford assembly line. Think about a very long time ago, before we had assembly lines. Cars were made by a handful of skilled craftsmen who made most of the car themselves. The great thing about the Ford assembly line was that it took all the tasks to build a car and it separated them out into individual jobs, meaning 90 people could work in unison to produce a car, all in one production line. You no longer needed a skilled craftsman. While this allowed Ford to hire what you would call lower skilled laborers, it also meant that somebody working a particular task got exceptionally good at that task. If you were the person assembling wheels, for example, let's say somebody did that, you were assembling thousands and thousands of wheels a year working on the assembly line, versus a skilled craftsman who maybe only did a few hundred because they were building the entire vehicle. By dividing out this labor, you would get skilled workers in every distinct task. And because that's what the laborer was doing with most of their time, they would find ways to improve that task. And while the improvements might be incremental, because of mass production, they would add up. So this division of labor and superior techniques would allow you to produce more for less, an economy of scale. Another determinant is known as learning economies, which says as tasks are repeated, the performer increases their ability to perform the task and can more readily introduce incremental innovations that lower the average cost. This is very similar to the division of labor and superior techniques. You call this trend of decreasing cost per unit the unit curve, and it can be expressed with a formula. Cn, the cost of whatever number unit you are producing, is equal to C1, the cost of the first unit, times n, the number of units, raised to the power of negative a, which is the elasticity of cost with regard to output. There are several types of elasticity. You are probably more familiar with the one on the purchasing side, or at least I was. An example of that being a product where the price changes greatly but demand stays the same, you would call that inelastic. The price does not affect the demand very much. On the flip side, if the price increases just a little bit and the demand drops dramatically, that is a very elastic good. Different goods have different elasticity values, and there's elasticity on the cost and output side as well. In the example, I chose bags of rice, and I just made up the cost elasticity, but you can see as I double the units, the bags of rice, you can see how the cost drops. In this scenario, every time the output doubles, the cost is reduced by about 3.5%. So you would call this a 97% experience curve, which says every time the units double, you can produce for about 3% less in cost. There are also growth economies, which occur when a company acquires an advantage by increasing its size. One cause of growth economies is resources or competencies that aren't fully utilized at one size, but can be better used or accessed when growth occurs. One example would be if a grocery store expands to a new location and they buy a big plot of land for that new location and only use part of it, they can then end up selling some of the excess land to shops that want to be near that grocery, which means they make some money back on their land and can evaluate that cost differently. If this grocery didn't expand and didn't open a second location, they would not take advantage of this extra land. Also, based on your industry, there are scenarios where you can increase your output without really needing to hire more people. For example, crews on ships, trains, airplanes, and certain types of manufacturing that are very machine heavy. You don't necessarily need more people just because your output has increased. And finally, depending on the area of business, sometimes you can have an economical use of byproducts as your production goes up. One example would be in the paper industry. Paper mills can burn bark and fine wood particles to produce process steam and to recover some of the pulping chemicals as well. It's not advantageous to do this cost-wise until your production hits a certain volume. And as is usually the case with my videos, this video has gone on for much longer than I anticipated, so I'll leave you with this. Other areas to explore. There are internal versus external economies of scale, how economies of scale impact the real world in relation to international trade, justification for business or market expansion, how they can lead to monopolies, etc. There are numerous historical figures you can look into that have talked about the economy and economies of scale, and there is a big relationship between economies of scale and timing. There is a rhythm of production and industry. Thank you so much for watching this video. I hope you now understand what economies of scale means, what some of the big determinants are, and how engineers help contribute to this. If you like this video, feel free to subscribe, and have a great day.